If you're going to be a psychiatric nurse practitioner, you know that understanding why a medication works is every bit as important as knowing what it does. So today, we're going to take a journey all the way from the symptoms you'll see in your office down to the tiny molecular machinery that psychotropic drugs are actually designed to target. Okay, let's get into it. This quote really frames our whole discussion. For decades, we all talked about a simple chemical imbalance. But the modern view, the one that really guides pharmacology today, is that psychiatric illness is a problem of brain circuits. It's about how entire networks of neurons are firing, or in a lot of cases, misfiring. And that's our starting point for today, this idea of psychiatric disorders as circuit-based problems. Once you start thinking this way, it completely changes how you see medications. They aren't just topping off a chemical. They're trying to retune an entire network. So here's our game plan. We're going to start with the basics, how one single neuron sends a message. Then we'll look at the different ways neurons can talk to each other. After that, we're diving deep inside the cell to see what happens after a message is received, how that leads to literally rewiring the brain, and finally, how all of this gives us the foundation for modern pharmacology. Okay, so let's start with the most fundamental piece of these circuits, the neuron itself. These are the real workhorses of the brain, right? They're responsible for every single piece of communication. If you want to fix the circuit, you've got to understand the messenger. So what exactly is a neuron? Well, in the simplest terms, it's a highly specialized cell that's built to do three things and do them really, really well. Receive a whole bunch of signals, add all that information up, and then make a decision about whether or not to pass that message along. And the flow of information is pretty straightforward. It starts at the dendrites. Think of them as the neuron's antennas. That signal gets processed in the soma, which is the main cell body. Then, the big go or no-go decision happens at the axon hillock. If it's a go, the signal zips down the axon, which is like a long transmission cable, all the way to the axon terminal, where it releases its chemical message. So how does it decide? Well, that neuron is constantly getting thousands of tiny electrical messages. Some of them are like hitting the accelerator. We call those EPSPs. They make the neuron more likely to fire, and others are like hitting the brakes. We call those IPSPs, and they make it less likely to fire. And this is the moment of truth. Down at the axon hillock, all those accelerator and brake signals get added up. If the total positive charge hits a critical threshold, bam! It's like pulling a trigger. An all-or-nothing electrical blast. The action potential shoots down the axon. There's no stopping it. And that's what causes the neurotransmitters to be released at the other end. But, it's not always that simple. That one-way street isn't the whole story. The brain is way more clever than that. Neurons actually have a few different ways of talking to each other. First, we have classic neurotransmission. This is the one we all learn first. The electrical signal arrives, it gets converted to a chemical signal, the neurotransmitter, which floats across that tiny gap, the synapse, and delivers its message to the next neuron. Most of the medications you'll be working with target this exact process. But it's not just a monologue. There's also retrograde signaling, where the receiving neuron actually talks back to the sender. It uses molecules like endocannabinoids, the brain's own cannabis system, to basically say, hey, got the message, you can quiet down now. And then there's volume transmission. Think of this like the brain's Wi-Fi. A neurotransmitter like dopamine can just sort of diffuse across a whole area, influencing entire groups of neurons without a direct connection. This is absolutely critical for understanding how we regulate things like mood and attention. Okay, so a neurotransmitter has crossed the synapse, it's docked with a receptor, mission accomplished, right? Nope, not even close. In fact, that's just the very beginning of a much, much deeper story. I absolutely love this quote from Dr. Stephen Stahl because it's just so true. That neurotransmitter, our first messenger, has just delivered a package to the front door of the cell. Now, a whole internal relay race has to get that message from the front door deep into the heart of the cell. This is the signal transduction cascade, what Dr. Stahl brilliantly calls the molecular pony express. The first messenger, our neurotransmitter, kicks off a second messenger inside the cell. That one activates a third, which activates a fourth, often by tacking on a little phosphate group. With each step, the message gets passed along and amplified. And this cascade is the perfect way to explain therapeutic lag to your patients. Some effects of a drug happen in milliseconds as ion channels open. That's why you get immediate side effects, like maybe feeling a bit tired.
But the real therapeutic changes, the ones that depend on this whole pony express reaching its destination and changing how the cell works, that process takes hours to days just to get started and weeks to really take effect.
So where is this Pony Express headed? What's the final destination? Well, it's headed for the command center, the cell's nucleus. This is where that initial, tiny signal from the outside can trigger massive, long-lasting changes that literally start to rewire the brain.
Which brings us to this incredible field called epigenetics. Now, this isn't about changing your actual DNA code. It's about changing which of your perfectly normal genes get turned on or turned off. Things like stress, trauma, but also positive things like therapy can add little chemical tags to your DNA that act like dimmer switches. It suggests that many mental illnesses aren't caused by bad genes, but by the right genes being turned on or off at the wrong time. And here's how it connects. That final messenger in our Pony Express can activate something called a transcription factor. This little protein marches into the nucleus, finds a specific gene, and flips the switch. And the result? The cell might start building more receptors, or sprouting new connections to other neurons, or making more growth factors. It physically changes the circuit. So let's bring it all home. We've gone from a big picture circuit problem all the way down to a single neuron, through a cascade of messengers, and right to the genes themselves. This whole biological journey, this is the real foundation of what we do in psychopharmacology. And here it is. This is probably the single most important takeaway. When you prescribe a medication, the goal isn't just to boost a chemical in the synapse. That's just step one. The real goal, the ultimate goal, is to use that chemical to kickstart this entire cascade to change gene expression and to cause long-lasting, enduring changes that heal the circuit. So I'll leave you with this question to take with you into your practice. Knowing all this, knowing that you're not just tweaking chemicals but actually starting a process of cellular repair and rebuilding, how does that change the way you talk to your patients about their medication? How does it change how you explain why it takes time? And how does it change how you talk about the amazing dynamic power of their own brains to heal?